By the end of this lesson, the students will be able to define the ionic product of water, Kw, relate the acidity of an aqueous solution with its pH value, define pH and pOH and calculate their values using the molar concentrations of H+ ions or OH- ions. Water is a covalent compound. The electrical conductivity of pure water is not exactly zero. What can you deduce about the composition of pure water from this observation? Answer: pure water must contain some ions. Pure water shows a slight ability to conduct electric current. These ions arise from the ionization of water itself. Let us look at how the self-ionization of water occurs. Click the Start button. Click on the container of pure water to view the particles present. Note that very few water molecules are ionized at any given instant. Pure water consists almost entirely of water molecules and is therefore a poor conductor of electricity. Click the Simplified button to view the simplified version of the equation for the self-ionization of water. Ionization of 1 mole of water molecules produces 1 mole of H+ ions and 1 mole of OH- ions. Click the Kc button. Click the Rearrange button. H2O is effectively a constant and thus can be incorporated into the equilibrium constant to give a new constant Kw. Kw is known as the ionic product of water. Its unit is mole square per decimeter power 6. The concentrations of H+ ions and OH- ions in pure water are equal. Click the 25°C button to find out the value of these concentrations at this temperature. Click the Substitute button and then Calculate button. The ionic product of water at 25°C is 1.0 times 10 to the power of -14 mole square per decimeter power 6. As it is an equilibrium constant, the ionic product of water varies with temperature. Summary: water undergoes self-ionization and gives a few H+ ions and OH- ions. These ions are responsible for the conductivity of pure water. The ionic product of water, Kw, is 1.0 times 10 to the power of -14 mole square per decimeter power 6 at 25°C. Since Kw is the equilibrium constant, its value varies with change in temperature. In pure water, the molar concentrations of H+ ions and OH- ions are equal. Click the Add HCl button. The molar concentrations of H+ ions and OH- ions are no longer equal. Why is this so? Answer: HCl ionizes in water to form H+ ions and Cl- ions. There are now more H+ ions present. The concentration of H+ ions is now higher than 1.0 times 10 to the power of -7 mole per cubic decimeter. The solution is said to be acidic. Although the molar concentrations of H+ ions and OH- ions are no longer equal, their product Kw is the same. What is the concentration of OH- ions in the solution? Answer: the concentration of OH- ions is less than 1.0 times 10 to the power of minus 7 mole per cubic decimeter. We can categorize solutions into acidic, basic, and neutral solutions based on their molar concentration of H+ ions. Click each of the boxes in column 1. The molar concentrations of H+ ions in an aqueous solution is usually very small. To make comparison of small values of concentration of H+ ions easier, we express concentration of H+ ions in terms of pH. Click pH button to view its definition. Drag each of the different values of concentration of H+ ions into the empty box in the equation. How does the pH change with an increase in concentration of H+ ions? Answer: the pH decreases with an increase in concentration of H+ ions. Now, click on each of the empty boxes in column 2. The diagram above shows the relationship between pH and concentration of H+ ions. The acidity of an aqueous solution depends on the concentration of its hydrogen ions. A Poh scale can also be obtained in the same way. We define POH as POH equals negative log of concentration of OH- ions to the base 10. Click the Start button to derive the relationship between pH and POH at 25 degrees Celsius. We can therefore find the value of either concentration of H+ ions or concentration of OH- if we know the value of the other. Summary: in pure water, the molar concentrations of H+ ions and OH- ions are equal. At 25 degrees Celsius, concentration of H+ ions is equal to the concentration of OH- ions is equal to 1.0 times 10 to the power of minus 7 mole per cubic decimeter, and Kw is equal to 1.0 times 10 to the power of minus 14 mole square per decimeter power 6. Kw is equal to 1.0 times 10 to the power of minus 14 mole squared per decimeter to the power of 6. Also applies to dilute aqueous solutions, even though the molar concentrations of H+ ions and OH- ions are no longer equal. The acidity of an aqueous solution depends on concentration of H+ ions. As the acidity of solution decreases, its pH increases. Acidic solution, pH is less than 7.0. Neutral solution, pH is equal to 7.0. Basic solution, pH is greater than 7.0. The pH of a solution is defined as pH is equal to the negative logarithm of concentration of H+ ions to the base 10. The POH of a solution is defined as POH is equal to the negative logarithm of concentration of OH- ions to the base 10. The relationship between pH and POH at 25 degrees Celsius is given as pH plus POH is equal to 14. The pH of an aqueous solution depends on the concentration of H plus ions present in it. Click on box A to view the particles present in a 1 mole HCl aqueous solution. Now, click on box B for a 1 mole acetic acid C2H5COOH aqueous solution. There are more H plus ions present in a 1 mole HCl solution than in a 1 mole acetic acid C2H5COOH. Discuss and click Next. More HCl ionizes or dissociates to form H plus ions than acetic acid C2H5COOH. Acids such as HCl and HNO3 are considered to be 100% dissociated in aqueous solutions. Such acids are said to be strong acids. HCl and HNO3 are also monoproctic acids which produce 1 mole of H plus ions per mole of acid. Calculating the pH of such acids is straightforward as the molarity of H plus of the aqueous solution can be obtained from the molar concentration of the acid. Click on box C. Enter the correct value into the empty box in the pH expression. Solution in box C has a higher pH value than solution A, as it is more dilute. A solution of a strong acid can have a higher pH value than one if its concentration is low. We can calculate the pH of an aqueous solution of a strong base given its molarity. Enter the correct value into the empty box. Enter the correct pOH value to calculate the pH. Summary: acids that are 100% dissociated in aqueous solutions are said to be strong acids. The molarity of H plus ions in an aqueous solution of an acid is equal to the molar concentration of the acid if the acid is a strong monoproctic acid. A very dilute solution of a strong acid has a pH higher than 1.